Subject code 19 MA203 Complex Variables and Differential Equations. Unit 3 Fourier Series. Course outcomes are: evaluate Fourier series for standard periodic waveform, that is, musics are converted into some waveform or sounds are converted into the waveform. So these are very important applications for converting the waveform like sine and cosine series. Learners should know this, know what a periodic function is, be able to integrate functions involving sine and cosine series, have knowledge of integrations by parts, periodic in nature for some functions. Overview of these topics are: introductions, definitions and formulas, problem based on 0 to 2 pi, problems based on 0 to 2l, even and odd functions, minus pi to pi and minus L to L, off-range cosine series, off-range sine series, harmonic analysis. So first we can go through the introductions and definitions based on the formulas. These are first sessions. So next remaining sections we will do in the next video notes. So first we shall go through the introductions and definitions. So before that I will tell here is which one is important topics, which one is easiest one. For harmonic function is a very easiest one when you know the Fourier series formula. So before that, problem based on 0 to 2 pi, problem based on 0 to 2l, these two are very familiar, means the harmonic analysis is a very easiest topic to learning process. So here is formula must be like a simple formulas. That formulas occurs the following sections: based on the 0 to 2l, even and odd functions, off-range cosine series, off-range sine series. So formula we have only one formula is enough. For changing the simple thing we will get the remaining formulas. Applications are signal processing, image processing, heat distributions mapping, wave simplifications, light simplifications and radiations measurements and so on. So these are very important applications tools using in the engineering field. For steady state response, the Fourier series of the response signals is determined by first finding the response to each component of the input signals. This is the first one. Next one is the individual response are added to form the Fourier series of the response signal. So any sounds they will be converted like a signals, that is a wave frequency form using the Fourier series. So these are very important applications for many field. They are using familiar things. So first we shall go through the introductions, definitions and formulas. First definition number 1. So define Fourier series. So the infinite trigonometry series a0 by 2 plus summations n equal to 1 to infinity an cos n pi x divided by L plus summations n equal to 1 to infinity bn sin n pi x divided by L is called the Fourier series of f of x in the interval c less than or equal to x less than or equal to c plus 2l. Provide the coefficients are given in the Euler's formula. So this is one formula is enough. This is based on the L. Then next one is based on the 2 pi formulas. So again I can tell here a naught by 2 plus summations n equal to 1 to infinity a n cos n pi x divided by L plus summations n equal to 1 to infinity b n sin n pi x divided by L. This is a Fourier series in an interval 0, that is c, 2L. Then provide the coefficient is given by the Euler's formula. So definitions 2. Definitions 2. Periodic functions. A function f of x is set to a periodic t, capital T, if for all x f of x plus capital T equal to f of x, where t is a positive constant, that is t is always greater than 0, is called the periodic functions of f of x. So t is a time period, so this is always like a positive, there is no negative terms here. Example, we know that f of x equal to sin x, that is equal to sin of x plus 4 pi. We can take some periodic is t is 4 pi, so x plus 4 pi and goes on. Therefore the functions as period 2 pi, 4 pi, 6 pi, etc. However 2 is the least value and therefore is the periodic of f of x. So periodic is always 2 is a least value, there is no in the single values here. So 2 pi and so on, 2 pi, 4 pi, 6 pi and so on here. Similarly we can construct cos x also. So cos x is a periodic functions with the period 2 pi and tan x as a period pi. For this case only tan only we can use in the pi here. But the Fourier series using only the two trigonometric functions, one is sine, one is cos. These two are very important. One, tan is not necessary to use in the Fourier series. Why means tan x does not get any the waveform here. So only sine and cos both are getting the waveform itself. Basic conditions and formulas. So these are very important conditions. So these conditions must be satisfied, means the Fourier series must be, we get the required solutions here. So Dirichlet's conditions. So these are very important 2 mark questions. State Dirichlet conditions. A functions f of x defined in c less than or equal to x less than or equal to c plus 2l can be expanded as a infinite trigonometry series of the form a naught by 2 plus summations a n cos n pi x divided by L plus summations b n sin n pi x divided by L, provided number 1 f of x is single valued and finite. Number 2, f of x is continuous or piecewise continuous with finite number of finite discontinuous. Number 3, f of x has no or, that is f of x has no or finite number of maximum or minimum in c, c plus 2l. So these 3 conditions must be satisfied, means the Fourier series, this required formula must be satisfied. So this name is Dirichlet conditions based on the Fourier series. So these are very important 2 mark questions. So next we can go through the Euler's formula. So what is Euler's formula? So if a function f of x defined in an interval c, c plus 2l can be expanded as the infinite trigonometry series a naught by 2 plus summations n equal to 1 to infinity a n cos n pi x divided by L plus summations n equal to 1 to infinity b n sin n pi x divided by L. Then where a n equal to 1 divided by L integral over c to c plus 2l f of x cos n pi x divided by L into dx, b n equal to 1 divided by L integral c to c plus 2l f of x sin n pi x divided by L dx. So a n is always based on the cosine function, b n is always based on the sine functions. This does not change for this whole unit. So these are very important formulas. If you are familiar, means just we can replace the notations only, they will get the different types of formulas based on the problem here. So where a n and b n are called Euler's formula for Fourier coefficient. So your question is Write down the Euler's formula for Fourier coefficient means we can write the statement is enough, then where an and bn also must be included. So these are very important 2 mark questions. So next we shall go through the basic formulas. So these are very important formulas for using the entire unit here. So sin n pi equal to 0. Next one is cos n pi equal to minus 1 over to the power of n. For example, here is put n equal to 1, 2, 3, any numbers. So answer must be 0 itself. For cos, n equal to even number means your answer must be plus 1. N equal to odd number means your answer must be minus 1. So be careful here. So sin n pi is always 0, cos n pi is minus 1 over to the power of n. These 2 formulas are very important one. Remaining is not necessary, but if you are using in the problem is I can tell later here. So next trigonometry formula. So what is sin A sin B? So 1 by 2 times of cos A minus B minus cos A plus B. So this 2 comes here. That is the original formulas, or we can write 2 sin A sin B is also right. Next 2 cos A cos B equal to cos of A plus B plus cos of A minus B. Then 2 times of cos A sin B is sin A plus B minus sin A minus B. So these things are very important formula based on the Fourier series trigonometry formula. And next one is this 11th formula is very important one, Bernoulli's formula. If you know this one only, you are able to write the solutions here. So integral uv dv. So here is we have did the mistake here. Integration of uv dx, not dv. So integration of uv dx equal to uv1 minus u dash v2 plus u double dash v3 minus u triple dash v4 and so on. That is alternative sign, positive negative positive negative. Start with u dash u double dash, start with v1 v2 v3 etc. So where u dash u double dash u triple dash are the differentiations with respect to x, v1 v2 v3 are integrations with respect to x. So these 2 things are important one. v1 v2 means integrations, u dash u double dash are differentiations. So I will tell in the problem here. Okay, so first I can give an example based on the Bernoulli's formula. So evaluate integral x square e power x dx. So here is how we can use the Bernoulli's formula. So integration of x square means we know the formula for that. Integration of x square is x cube by 3. But here is one exponential form, one function is given. So one trigonometry form or one variable form. In the mari kuduthirundanga, we can use in the Bernoulli's formula. So for in this Bernoulli's formula, we can use always u equal to the variable x square x cube adu mari ikkira terms alla u use pananum. V is always trigonometry form or exponential form. This rendu use panikalam. So ipo enna kuduthirukanga, given integral x square e power x dx. So using Bernoulli's formula, integral uv dx equal to uv1 minus u dash v2 plus u double dash v3 minus etc. We can take this one as equation number 1. So already I told u dash u double dash triple dash are the differentiations, v1 v2 v3 are integrations. So now we can take u equal to, I can take x square, v equal to e power x. So first derivative u dash, differentiation of x square is 2x. Second derivative, differentiation of 2x is 2. Third derivative is 0. So v equal to e power x. What is v1? Integration of e power x is e power x. What is v2? Integration of e power x again e power x. Suppose v3 means integration of e power x again e power x. So substitute this value in equation number 1. Therefore integral uv dx equal to uv1 minus u dash v2 plus etc. So replace the value here. U is in terms of x square, v1 is in terms of e power x, then u dash v2, then u double dash v3. Then last term must be in 0, we can leave it. So next you can simplify this one. We get e power x into x square minus 2x plus 2. So this is a simple basic example for Bernoulli's formula. If we are familiar with this one means we will do more problem here without doing any mistakes here. So these are basic things we have to write and learn again and again. So finally, the applications based on the Fourier series. Here I will play one video based on the Fourier series applications. So just we can watch here.
There are these things called Fourier series. In a manner of speaking, they're a way of taking a complicated whole and viewing it as a sum of its simpler parts instead. Fourier series facilitate models of natural phenomena. Ancient Greek astronomers theorized that the Earth lay at the center of the universe, with the moon, sun, and heaven. There are these things called Fourier series. In a manner of speaking, they're a way of taking a complicated whole and viewing it as a sum of its simpler parts instead. Fourier series facilitate models of natural phenomena. Ancient Greek astronomers theorized that the Earth lay at the center of the universe, with the moon, sun, and heavens rotating around it in perfect circles. However, when they looked into the night sky and observed how the moon and planets were really moving, they realized that the motion was inconsistent with their theory. Taking the moon, for example, if the moon was moving in a circle, like in the Greeks' theory, it should always be the same distance away. So why did it appear darker on some nights and brighter on others? It was also bigger on some nights and smaller on others. The Greeks had to change their hypothesis then. What if for each heavenly body there was a smaller circle rotating around a bigger circle, and the body was rotating on that smaller circle? But again, what they saw in the night sky just didn't match up. So the astronomers started adding circles on circles on circles, until they had a model of celestial motion that matched what they saw in their observations. It's known today that orbits are ellipses, not circles on circles. So how did the Greeks' incorrect theory match what they observed in the sky? The answer is Fourier series. Adding up the many circles, the parts, allowed the Greeks to model celestial motion, even without understanding the true elliptical paths. In math, orbiting around in a circle can be represented as the orbit is equal to r times e to the I omega t, where e to the it represents moving in a circle. The Greeks in their theory, though, had circles of different sizes and rotation speeds. This is where the other variables come in. The r represents radius and controls how big the circle is. The omega represents angular frequency and controls how fast the circle rotates around. Representing circles rotating on circles is simply adding up more of these terms. When we add more and more, reaching an infinite number of circles, we now have what is called the Fourier series of the orbit. Ultimately, the Greeks weren't right about how orbits worked. What they ended up doing was constructing a Fourier series approximation of the real elliptical orbits. Sure, Fourier analysis can create an ellipse approximation, but it can create really any shape too. The right arrangement of circles can make an orbit in the shape of Homer Simpson's face. Something important to note is that an orbit can be thought of as anything periodic. That is, something that repeats itself over time. So Fourier series can take anything periodic, like a waveform, and analyze it as sums of circles. From the unit circle, it's also known that circles are basically sines and cosines. Taking these two ideas together puts Fourier series in its more familiar form, as sums of sines and cosines representing waveforms. A lot of complex nature can be represented this way. The planets are not the only example. While Fourier series allowed a human civilization to model and simplify nature, it also allows nature to model and simplify nature. Your own body is performing Fourier analysis just listening to this video. Ears make Fourier series to process sound. Inside the inner ear are thousands of hair cells of varying lengths. Because the hairs are different lengths, they resonate at different frequencies. For example, long hairs will pick up waves with lower frequencies, and short hairs will pick up waves with higher frequencies. When a complex sound wave enters the ear, the hairs help the brain break it down into individual frequencies. Instead of the total sound wave then, the brain sees a bunch of simple sinusoids with different amplitudes and frequencies, and then combines them to process sounds. Rather than taking the actual sound wave as a whole, the brain is able to process the same information by analyzing individual sinusoids. Just like how the Greeks understood planetary motions as individual circles rather than actual ellipses. Behind the equations of Fourier series lies a means of representing many aspects of nature. The Greeks unintentionally used Fourier series to simplify their science. They didn't understand the true nature of orbits, but were still able to use sums of circles as a matching model. At the same time, the human body creates Fourier series naturally and subconsciously. Rather than processing the true sound wave as a whole, the brain is able to process sound using individual sinusoids. Fourier series are everywhere, and ultimately they're a tremendously powerful tool used for breaking down complicated phenomena into more understandable approximations and models.